In this lecture, we discuss how do we evaluate the classification algorithms we have designed so far. So, we have looked at three classification algorithms so far. One was the decision tree algorithm, one was the Bayesian classifier, and then we studied the nearest neighbor classifier for some value of k. So, now the question is that how do we know that which classifier to choose, which one is better, which one should choose. It turns out that depending on the problem you are solving, some classifier, there is no classifier which is good for all the problems. Some problems, some classifier is good, some other problem, some other classifier is good. So, it is very important to have quantitative or objective measures of telling how good a classifier is. So, that is what we will discuss in this talk. So, we will discuss three aspects. One is we define some equation, some metric which given a classifier and a problem, it will tell how good the classifier is at that problem, it will give some value. Okay. So, different type of ways we can evaluate. So, for example, suppose you are a student has given the exam and he has got so many subjects are there and he has got this amount of marks in each, this percentage of marks in each of the subjects. How do you tell? Do you consider the average of all marks? Do you consider the highest of all marks, and so on? So, different ways you can evaluate. Second is once you have defined the performance measures, how do I compute them? Rather, how do I estimate their value in a faithful manner? Okay. So, one is say for example, when you are evaluating a student, one is saying what defines how good a student is. Second is do you take actually tests, maybe a unit test and say maybe 5 tests an year, and to consider the marks of each of these tests to properly estimate these measures that we have defined. And the second is, now given these measures and their estimates, how do you compare two algorithms? Okay. So, among algorithms, this is actually not an easy problem, because maybe with respect to some measure one algorithm is better than the other. Okay. Say maybe in maths one student is better than has got more marks than the other, but maybe in history another measure, some other that student has got more marks than this. So, if there are multiple measures, it is difficult to say that which algorithm among this. So, some aspect of some algorithm is good, other aspect of some other algorithm is good. So, how do you compare? That is what we will discuss in this second aspect, third aspect. Okay. So, before that, let me tell you what is a classification task basically. So, what you have is let me make the picture clear. So, what you have So, we have a training set on n training instances and you have a learning algorithm, say a Bayesian classifier or something, which gives you a classification rule. Okay, gives you a classification rule. What does the classification rule do? If you take in a new instance x whose y is not known, note that in the training instance I have a set of x whose class labels I call y is already known. Supervised learning, we know the class labels of these instances. Okay. And then what this classifier does is that it predicts the class level of this new example x. So, it predicts y, let me call it as y hat, predicts y. Okay. So, these algorithms, that is why are also sometimes called predictive data mining algorithms. Okay, they predict. Now, what these performance evaluation metrics do is that it evaluates this classification rule in terms of how good this prediction matches the actual value. Okay. So, for example, I am predicting a 2 class problem, maybe I am predicting tomorrow there will be rain or there will not be rain, there will be rain or there will not be rain. Okay. So, there are 2 classes, rain or no rain, and my rule say predicts rain tomorrow. Today it predicts that tomorrow it will rain. I will say my prediction is correct, it has done a correct classification if it matches tomorrow's fact, that is tomorrow it has rained or not, and I will say it is misclassified if it does not match. Okay. So, that is the main intuition. So, we basically find and this what I do, I do not do for one instances. Suppose goodness will be not just for a single instance, even though I will need it only for a single instance, is for if you do it 100 times, how many times it matches the actual prediction. Okay, in what percentage of the time it matches the actual prediction. Okay. So, one step to compute this matrix is to construct what is called a confusion matrix. Okay, what is called a confusion matrix. So, what is a confusion matrix? It is a, suppose for a 2 class problem, it is a okay. So, it is a 2 by 2 matrix for a 2 class problem. So, how do I get the matrix? I get the matrix in the following way. So, what I do is that of consider a test set of m examples. Whose class levels I know. And let us say a number out of these m examples actually belong to the first class, let me call it as a S class, and also predicted to be S class. Okay. So, a out of m, a out of m, and this number I would call it as a true positive, actually positive, also predicted as positive. These actually are it is the most desirable case. Then we consider B, which is actually positive classified as negative. Okay. Actually positive classified as negative. I call this a false negative. Similarly, C is false positive and D, which is true negative. Okay. So, it is this A and D which are correct classifications. These are two types of errors. You can also easily think that m equals sum of this. Equals the sum of this. All right. So, this is the fundamental. So, how many this we can easily extend, like I can like this. This is actual and this is predicted along the rows actual and along the columns predicted. So, you have class 1, class 2 and so on and so on. Okay. So, I can extend this concept and the diagonal is the correctness. Okay. So, this is the fundamental thing. Now, using this confusion matrix, I can define several metrics. Okay. So, using this true positive, true negative, false positive, false negative. I can define several measures. The most common is accuracy. So, it is the sum of the diagonal elements divided by total number of elements. Okay. So, this by this, fine. You accept that this is a good measure, important measure. What else? So, one I am just defining, it is a very important measure. But only this is sometimes misleading. Take this example. If the classes are imbalanced, sorry, this may happen. Okay, this is clear. So, I introduce another matrix called a cost matrix, cost of each type of error. Okay. So, C is the cost. This is what I want. So, now I can have several cost sensitive measures using the cost matrix as well as the confusion matrix. Okay. You may assume uniform cost also. Precision, if you go back, it is this by this. Okay. Similarly, you have recall, which is A by A plus B. Okay. So, these are two measures commonly used. We have a combination of precision recall called F measure. So, it is the harmonic mean. It is the harmonic mean. In general, you can have a weighted accuracy. Remember the cost matrix where I have a weight as costs, and so just accuracy is W1, W2, W, all these are 0, 1, all these are equal and 1 accuracy. If this is equal to 1, this is equal to 0, then weighted accuracy equal to precision. Okay, equal to precision. Similarly, if this is equal to 1, this is equal to 0 and this is equal to 1, 0, 0, 1, you have recall. Okay. Now, the next question, how to get a estimate of this accuracy, precision and so on. What size training set you, test set you need? Okay. These are the methods. Okay. So, this is cross validation, the most common method. Okay. These are the steps: partition, train, k-fold, do it, average you take. So, this is clear, the cross validation method, how to estimate it. Each of these methods gives a good method of estimating. So, what you do, you take a training set, on that you find this, take several training set, take the average of these values, that is a good estimate. Okay. How do you compare models? ROC curve. This is the definition: true positive, false positive. Okay. And this is important. All right, so this looks like this. So, area under ROC curve is a good measure. Okay. So, these are the measures. So, I am not listing all of them, you can go through them. Okay. You can go through them, test of significance, many things. So, that is how you measure it. So, I think you have got an idea of how to evaluate the classifiers if you have a training set and a test set, and these are commonly used for the classification. Okay. So, if you apply this classification algorithm, you have to use this. All right. So, thank you for today. We will go into the next topic in my next lecture. Thank you.